Imagine opening a single file and finding three complete reasoning models inside it. One handles quick queries, another balances speed and depth, and the third delivers maximum accuracy. You might think this is science fiction, but it is the reality Nvidia is pushing with their Nemotron elastic framework. The problem is that most teams today manage separate weight files for every latency budget, creating a nightmare of storage costs and deployment complexity. By the end of this video, you will understand why a single checkpoint could be the missing link that finally solves production model sprawl. For years, the standard approach to serving AI models has been to build a family. You train a large model for high accuracy, a smaller one for speed, and maybe a medium one for balance. Each one requires its own training run, its own dataset, and its own set of hyperparameters. When you deploy these to production, you end up with multiple large files sitting on your storage servers. Every time you need to update a model, you have to retrain, revalidate, and redeploy the entire family. This creates what engineers call model sprawl. It is a failure mode where teams accumulate redundant weights for similar architectures, leading to wasted storage and the constant risk of version drift between your fast and accurate deployments. Here is the thing about model sprawl. It is not just a storage issue. It is an operational bottleneck that slows down innovation. When you have to manage separate registries for different latency tiers, your CI and CD pipelines become fragile. You spend more time moving files around than actually improving the intelligence of your system. The trade-off has been that you could never have both simplicity and flexibility. You had to choose between a massive, slow deployment that handles everything or a lightweight, fast one that lacks depth. The Nemotron elastic framework challenges this fundamental assumption. It introduces a concept where a single checkpoint contains multiple nested submodels. Think of it like a Russian nesting doll, but instead of dolls, you have layers of neural network capacity. A parent model of 12 billion parameters can host a 6 billion parameter variant inside it without any retraining. The architecture uses a hybrid of Mamba and attention mechanisms to preserve reasoning quality across all slices. This means the smaller slice is not a compromised version. It is a fully functional model that retains the core capabilities of the larger parent. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This capability is called zero-shot slicing. It allows the system to dynamically route requests to the optimal model slice at inference time without redeploying or swapping weights. If a user asks a simple question, the system instantly activates the 12 billion parameter slice, or even a smaller variant if available. If the query requires complex reasoning, it seamlessly switches to the full 30 billion parameter capacity. All of this happens within the same deployment container. The memory footprint remains constant regardless of which model size is active. This eliminates the need to store multiple copies of the same architecture on your servers. Now consider the cost implications of this approach. Traditional methods of building model families from scratch require training each variant independently. This is incredibly expensive. The research shows that this elastic approach achieved a 360 times cost reduction in training compared to building model families from scratch. Even when compared to state-of-the-art compression techniques, it offers a 7 times improvement. These numbers are not just theoretical. They represent a fundamental shift in how we calculate the return on investment for large language models. However, there is a nuance you need to understand about the implementation. The system relies on a specialized router to manage the slicing. This router determines which slice should handle a given request based on latency budgets and accuracy requirements. This introduces a potential inference latency overhead that must be weighed against the storage and management gains. You're trading a small amount of processing time for a massive reduction in operational complexity. For most production environments, this trade-off is highly favorable. The real breakthrough here is how this changes your disaster recovery strategies. Because you have a unified checkpoint format, your backup and restore procedures become significantly simpler. You do not have to worry about ensuring that the 30 billion parameter model and the 12 billion parameter model are perfectly aligned in versioning. There is no distribution shift between separately trained variants because they are all part of the same parent. The reasoning capability remains consistent across all slice sizes. This stability is crucial for teams that need to guarantee performance in critical applications. This technology also enables immediate A/B testing of accuracy versus latency trade-offs in live production environments. You can deploy the elastic model and then dynamically adjust the routing logic to test different slice configurations without ever touching the weights. You can see which balance of speed and accuracy works best for your specific user base in real time. This removes the traditional requirement to train and store separate fine-tuned models for each performance budget. It turns what was once a rigid deployment strategy into a fluid, adaptive system. There is a critical detail regarding the specific model sizes you might encounter. While the underlying technology validates the narrative of a many-in-one solution, the exact naming conventions and specific configurations like 30 billion, 23 billion, and 12 billion variants require verification against official announcements. The academic papers and GitHub repositories confirm the elastic architecture and the zero-shot slicing capability, but the specific product naming might evolve. The core principle remains the same, a single file hosting multiple nested models. This approach directly addresses the pain point of over-provisioning GPUs. Teams often provision hardware for peak accuracy requirements, leaving those powerful resources idle during periods of simple queries. With elastic slicing, you can utilize the full capacity of your hardware only when the task demands it. The system scales down the active model size when the task is simple, freeing up resources for other processes. This dynamic utilization is the key to making large language models economically viable at scale. The implications for junior engineers are profound. You no longer need to spend weeks managing multiple model registries. You can focus on the logic of your application and the quality of your prompts. The infrastructure complexity is abstracted away by the Elastic framework. This allows you to build more robust systems faster. It shifts the focus from managing artifacts to managing intelligence. The future of MLOps is likely to move towards this unified checkpoint paradigm. As the technology matures, we will see more tools that leverage this elastic architecture to simplify deployment pipelines. The ability to swap model sizes on the fly without redeployment will become a standard expectation for production systems. This is not just an optimization, it is a fundamental rethinking of how we package and serve artificial intelligence. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.